All right, let's see here. Scoot that over. Last day, we went through and we talked about just the general steps of hypothesis testing, right? And then, all right, so in terms of some quick review, right, we talked about the general steps of hypothesizing or hypothesis testing rather. Okay. And then we introduced an example, which I'm going to use to just kind of guide you through the particular steps of hypothesis testing for a single proportion or one sample proportion. So now, continuing with the example introduced last day. I'll just nab this and wait. This and then what we got to was to here. So we established that this is a one sample proportion type of question, which later you'll find really sets us on a path of how to solve this problem. Okay, for now, that's all we have, right? And so it's a little bit tricky. Okay, but we talked about why it's one sample proportion type of question. And then where I ended off was, okay, in order to check the conditions, we're going to need to state the null and alternative hypotheses first. And the reason for that is because we use the value from the null hypothesis to check the conditions. Okay. So let's see here. The null and alternative hypothesis, so far, what we've said is that for the null hypothesis, H naught, the null hypothesis, is a statement of no change. Okay, and so it's always going to have an equal sign. Okay, and then the alternative hypothesis is typically the thing that we want to prove. Okay, so for our questions, or for our question, okay, we're going to start with step one, which is state the hypotheses. Okay. How I would probably start is I would start by saying H naught and then HA, remembering that these are statements. So we use colons here, right? Just kind of setting the stage. And then really what I'm doing is I'm filling in the blanks here. And this is always going to be where you start. In fact, we can even start with putting an equal sign in the null hypothesis, even though we don't know anything about the null hypothesis yet, right? But we did say it'll always have an equal sign. And we can get more sophisticated with that later, but for us, an equal sign is just fine. Okay. Now, for one sample proportion, remember, we're trying to use the sample information to try to learn about the population, right? So if I have a sample proportion, really what I'm trying to do is I'm trying to use that to learn about the population proportion. Okay. So here, I'll say for one sample proportion questions, we are trying to learn about the population proportion, P. about the population proportion P, which means that is what we're hypothesizing about. So P goes here. P is the population proportion, right? So we don't hypothesize about the sample, right? Because we know we have the entire sample. We can calculate, we can find anything we want in the sample, right? That's not interesting, right? We want to know about the population proportion. Okay. And in general, okay, our null hypothesis, and I'll write it off to the side here, is going to be that P is going to be equal to some P naught. Okay, so some null value of the population proportion. Now this is going to be a value, okay, where P naught is a value or a proportion from the question. It's going to be the value we want to compare our sample proportion to. I'll follow that up here. P naught is the proportion we want to compare our sample proportion to. So I guess I should close the door here. Competing with anyone. All right. So from the question, right? If we reread it, 400 students were randomly sampled from a large university and 289 said that they did not get enough sleep. Conduct a hypothesis test to check whether this represents a statistically significant difference from 50%. Okay. And then we're told to use a significance level of 0.01. Okay. So if we want to know if 289 out of 400 is significantly different from 0.5, right? That makes this 0.5 or 50% our P naught, right? The value that I want to compare my sample proportion to. So that makes this 0.5 in this question. Okay. So here, this is my P naught equals 0.5. Okay. Now, our alternative hypothesis has to be about the same thing, right? If your null hypothesis is how P compares to 0.5, right, then your alternative has to be how P compares to 0.5, right? The only thing that's changing here is the sign or the inequality. Okay. So this is the only thing that changes. Otherwise, once you've decided, right, that it's P here, then it has to be a P here. And if it's 0.5 here, it has to be 0.5 here. Right. So once you have your null hypothesis, then you're off to the races, because you just have to decide what sign you have in the alternative hypothesis. Now that's going to come from the question. Okay. We have three options, and I don't think, no, we didn't get this far. Okay, yeah. So we have three options. Okay. Alternatives to equal to, kind of not equal to is a good first step, right? Or less than or greater than, right? So here we have three options. We have three options for the sign in HA. We could have not equal to, which is if we want to know if there's a difference. can have less than or greater than So depending on the question, we're going to choose what sign we have in the alternative hypothesis. Now, what's kind of tricky for most people is that this is information. So the sign that we have here, we're going to need it way later in step 3. Okay, and so that connection is tricky for a lot of people. Okay, and this is where we say, okay, if it's not equal to, so if I just want to know if there's a difference, then that's going to be what we call a two-sided or a two-tailed test. Okay, two-sided or tailed test. Because at some point, right, I don't care if it went way into the lower tail or way into the upper tail, right? If there's a difference, right, it doesn't matter which side it went into, right? So I don't care which tail. Whereas if I want to know if it's less than, right, then I'm in the lower tail, or greater than, then I'm in the upper tail. And this is for my p-value, right? Remember, this is our first question, so it is going to be weird. But these two, right, if I'm only concerned with one extreme, right, then I say it's a one-sided or one-tailed test. I usually call them two-sided and one-sided, but I guess two-tailed and one-tailed makes more sense because eventually this is going to translate to areas in the tails, right? Do you need one tail area or do you need both, right? Okay, so for our question, right, we want to know if there's a statistically significant difference from 50%, right? So here, this means that my alternative is that P is not equal to 0.5. Okay. Which means that I have a two-tailed test, okay, which I'll usually jot down here, two-tailed test. That's more of a reminder to myself later on. So we parking lot that up here, and then we're going to refer back to it later. Okay. So there's our null and alternative hypotheses. Okay. The difference between confidence intervals and hypothesis testing is that for our conditions, right, or our assumptions, we're going to use P naught to check these assumptions instead of P hat. It's such a small change, but it can be kind of, it's pretty confusing, I think. Make sure I didn't skip anything because I kind of went rogue. Okay, so put it on a fresh page here. So conditions for hypothesis testing, right, are now going to use P naught, right? Because we do all our hypothesis testing assuming that the null hypothesis is true, and the null hypothesis says that P is equal to P naught in general, right? So then we say, okay, well, I'm going to assume that P is equal to 0.5, right? And that's how I'm going to check my conditions. So conditions for hypothesis testing are now going to use P naught instead of P hat, which was for confidence intervals. Which means that P hat is now going to follow a normal distribution centered on P naught the null hypothesized proportion with a standard error of P naught Q naught over N. Okay. Kind of sneaking the conditions in as a sub-step of step one. It's not really a step in my usual steps. But I guess we can call it step 1B. How about that? Check the conditions. Our conditions are the same as for the confidence interval. As soon as we're dealing with a sample proportion, right? Does it follow a normal distribution? Then we're going to check the same conditions, which are independence and then the success failure condition. But that success failure condition is going to be using P naught, whoops, instead of P hat this time. So first condition is independence. We can assume that these students that were sampled are independent if they were randomly sampled. So let's go back and read the question. 400 students were randomly sampled. Hey, that's great. Right, so that's check. Even if it didn't say that, right, then we would have to assume that they're independent, right? So either way, you have to say that you assume they're independent. So students were randomly sampled. Therefore, we can assume independence. Our second condition is the success failure condition. This is the part that uses P naught to check the conditions instead of P hat. So that's why we need to state our null and alternative hypotheses before we can check the conditions. Although once you get more comfortable, you'll be able to source out your P naught, right? Then you can check your conditions before you state your hypotheses. But technically in your mind, you're finding that P naught, which is part of the null hypothesis and alternative, I guess.
P naught is a sample proportion.
Exactly. So here, use P naught instead of P hat. But the idea stays the same. We're going to check that N times P naught. Okay. And maybe I'll give myself a line here so I can draw above it. N times P naught, where P naught, like I said, is from the null hypothesis that P is equal to P naught. In our case, N was 400 students and P naught was 0.5. Even I can do that in my head. 200, which is of course greater than or equal to 10. So that checks out. It'll always check out for these questions that we're doing, right? It'll always check out. And even if it doesn't, there are ways to deal with that, but we're not going to tackle those, right? But we still have to do it because in real life, they're not necessarily going to check out. They're not curated like they are here. Okay. And really, what are we making sure? We're just checking that if P naught or if Q naught is a really rare event, right? Making that P really, really small, then we need to have sampled enough people to be able to detect that, right? To be able to detect at least 10, right? Otherwise, we don't have enough of a sample to draw conclusions. Okay. Which means that the failure condition is the same n times q naught, which is again 400 times 1 minus 0.5, which is still 200, which is still greater than or equal to 10. Now, because these conditions check out, right, they're all good, then we can assume, right, that p hat follows this normal distribution. So therefore, we can assume that p hat follows a normal distribution centered on p naught with a standard error of p naught q naught over n. If we know it follows a normal distribution and we know the center and we know the spread, right, we know how to solve problems like that. All right. So here, what this is saying is that, okay, p hat is going to come from a distribution that is normal, right, is centered on p naught, and a spread, the standard error of p hat is the square root of p naught q naught over n. Because we have n, we have our null hypothesis, right? And p naught. So we have all that information. Right? So now what we want to do is we want to look and see, okay, well, where does our sample proportion fall on this line, right? Is it within some reasonable realm of p naught, or is it far enough away from p naught to be considered statistically significantly different from p naught? Okay. So the idea here is that typically within some bounds, plus minus 2 standard errors typically. Okay. Here, everything is, approximately p naught, right? Close enough to p naught, not statistically significantly different. Whereas out here, right, this is where, as we move into the tails, right, that's where we're going to reject h naught. Right. So if you think of this center as the table, and I'm the sample statistic, right? If I'm standing here, I'm at the table, right? And then even if I'm standing here, I'm still standing by the table. Hey, where's Emily? Oh, she's over there by that table, right? Over here, it gets a little fuzzier, right? But I'm still kind of by the table, right? And then at some point, right, we all have this kind of imaginary line where we say, okay, well, that's too far. She's not over by that table anymore. She's over by this table, right? And so that's the equivalent as I'm moving away from the table, right? I'm moving further and further out into the tails, right? Making it less likely that I'm at the table, or the sample proportion came from a population centered on p naught. Oh, she had to go and say it like that. I know. Okay. That's what it is. Okay. So in this example, right, what's our p hat? In this example, p hat is generically denoted by x over n, right? The number of successes over n. And just so we don't have to scroll around too much, That's going to be 289 over 400, which gets me a reasonable number of 0.7225 without even rounding. That's it. So I'm going to keep it like that. So the question is, right, 0.7225 is different from 0.5, obviously, right? But is it significantly different from 0.5? And that's what we want to find. How do we decide that? Well, how many standard errors is it from 0.5? Yeah. Which leads me to step 2, do the test, do the do.
That was all step 1.
Yes, but I blabbed a lot. You do have to check the conditions, which I kind of introduced midway here, but I did blab a lot because really the only thing that's truly part of step 1 is that. Okay, so there's a lot of kind of ins and outs going on here. And you have to check the conditions at some point. Okay. But that's really all there is. Okay. And then now step 2. Do the test. Or if you want to be boring about it, you can say calculate the test statistic. But I really have a hard time saying test statistic, so I tend to avoid it. Calculate the test statistic. Okay. So if I want to see how far p hat is from p naught, taking into account the standard error of p hat, I don't know, that feels like a z-score to me, and it is. So no surprises there. Z is equal to p hat minus p naught divided by the standard error of p hat, which is now p naught q naught over n. Right, for hypothesis testing, we leverage that hypothesized proportion. So notice here, right, we're assuming the null hypothesis is true by using p naught in our test, which is what we were supposed to do. Okay. So now it's a matter of plug and chug here. And so Z p hat was 0.7225 minus p naught, which is 0.5. Okay. And then my standard error is 0.5 times 1 minus 0.5, which is of course 0.5, divided by 400. I've got these pre-baked, so ready to serve. Maybe I watched too many cooking shows. 0.2225 divided by 0.025. Don't forget to take the square root. Now, one bummer with picking a question, just kind of, this one seems nice, is I did not check the Z, and it's going to be quite large, but I think that'll be good because it's one of those things that people struggle with. So maybe it's good to start with this one. We'll see. But we get a Z of 8.9, right? So already in our minds, right, we're going to say, okay, well, that's more than 2 standard errors away, right? In fact, it's 8.9 standard errors away. So that's really far from the null hypothesized proportion. Right, so already I'm gearing up to reject the null hypothesis, right, because it's so far away to have happened just by chance. Okay. But we go with the flow, and nothing to it but to do it. Okay. So we've got our Z-score, this is our test statistic. This tells us how far our sample proportion is from our hypothesized proportion. Okay, so I was gonna do a little graphic, but I'll move it into step 3. See how fun step 2 was? Now that's a good step. Step 3, find the p-value. Remember the definition of the p-value is the probability of seeing something as extreme or more extreme than what you saw, right? Assuming the null hypothesis is true. Okay. Maybe let's remind ourselves of that. The p-value is the probability of seeing something as extreme or more extreme than what you saw, assuming H naught is true. Okay. Which really just translates to, okay, so it's a probability, so it's an area under the curve. And in fact, if it's as extreme or more extreme, that's the area in the tails, right? So then therefore the p-value is the area in the tails. And maybe I should do the S in brackets because this is where we track back to the alternative hypothesis, right? If I have a one-sided or one-tailed test, then I only find the area in one of the tails, right? Whereas if I have a two-sided or two-tailed test, then I replicate one of the areas in the other tail. So what does that look like? In general, if I've got my center, now I've got a Z, so Z is centered on 0. Okay. If I've got a Z score of something crazy like Z equal to 8.90, remember Z has 2 decimal places, right? So that's 8.9. Did I write? Yeah. Use 8.90. So what we want is we want to have this area in the tail as extreme or more extreme, right? So that's going to be our one-sided p-value. Okay, this is going to be our one-sided p-value. Okay. But for a two-sided p-value, remember we have a two-sided test because we want to know, is p different from 0.5, right? So then what we do is we just replicate what happened in one tail in the other tail. Remember, you only have one sample proportion, so it's going to happen in one of the tails, right? Or on one side of 0. So regardless of on if it's the lower side, then you replicate it on the upper side, or in this case, it's on the upper side. So then we replicate it on the lower side. Z is negative 8.90. I guess it's negative Z. Okay. So here, for a two-sided test, we replicate the test statistic in the opposite tail. We replicate the test statistic in the opposite tail. Yeah. So really what we do is to find, so this is going to be the one-sided p-value that we're finding, right? But if I need to replicate that in the other tail, I just multiply it by 2, right? So you're always going to start by finding your one-sided p-value, and then you're going to replicate it to find the two-sided p-value. To find the two-sided p-value, we take the one-sided p-value and multiply it by 2. And multiply it by 2. Okay. Now I've drawn 8.9 kind of close and visible so that we can talk about it, right? But really what's going on here, right? What does this curve look like? Right. 8.9 would be somewhere out here. Right, so it would be way, way out in the tail, but we don't need to be that specific, right? I'm just using the normal distribution to visualize the problem, right? So, okay. Okay. A Z of 8.9, how are we going to find the area in the tail, the one-sided p-value? Well, we can go to the Z table and we can find the positive side, right, and go down. But then we find that it maxes out at 3.49, right? So the Z table maxes out at 3.49. That's fine. That doesn't mean it ends, right? These tails go to infinity, right? So there's always some amount of area, but at 3.49 and negative 3.49, someone decided that's enough, right? The area in that tail is so small. In fact, it's going to be less than 0.0002, right? 3 zeros, right? Because this is the area to the left. So the area to the right is going to be 0.0002. So let's, running out of colors here. Okay. Maybe I'll draw a fresh curve. Fresh curve. So here it's centered on 0. And we've got our Z equal to 8.90. But then the table maxes out at Z equal to 3.49. Right, this is a number line centered on 0. And so 3.49 is to the left. And so here we can, with a little bit of practice, we can see that, okay, this area to the left is 0.9998, which makes this area 1 minus 0.9998, which is 0.0002. Okay. So what does that mean in terms of the area to the left or in the tail from 8.9? Well, all we can really say is that it's less than 0.0002. Okay. Sometimes we get a little sloppy and we say approximately 0, but it's really important that you say approximately 0, right? Because even though 8.9 is large, it's not that large compared to infinity, right? So there's area going all the way to infinity, and so you want to say approximately 0. So here, then this area to the left, we say is less than 0.0002 or approximately 0. And here, I'm gonna say, it's important we say approximately 0. Since the tails extend to plus minus infinity. Since the tails extend to plus minus infinity. In theory, obviously, right? Anything can happen is really what's going on there. Okay. So depending on how particular you want to be, right? Less than 0.0002, that's an answer for the one-sided p-value, or you can say approximately 0. Obviously, it depends on how the question is programmed, right? But there'll be instructions usually. Okay. And so less than 0.0002, even if I replicate that in the other tail, right? Then I'm gonna have less than 0.0002 times 2, so less than 0.0004, right? Or if you flip it, right, if you approximately 0 times 2 is still approximately 0, right? So therefore, the two-sided p-value is going to be less than 0.0002 times 2, which is less than 0.0004. That's an answer, right? Or it's going to be the two-sided p-value is approximately 0 times 2, which is still approximately 0. Less than 0.0004 is approximately 0, right? And so these are the same. It just depends on how you prefer to word it. So there's a little bit of finesse going on, trying to find our p-value. Usually you're going to have a z-score that would be in the table, right? That would be a lot easier, right? But here I'm kind of throwing you in the deep end, sink or swim type of situation. But I'm here holding your hand. All right. So that happens a lot where there are some questions where the z-score is not on the table, but now you know how to deal with it. Right. So now we have our p-value, right? Regardless of which one you prefer. Right? Now we can draw our conclusion. So step 4 is the conclusion. The conclusion has 3 parts, right? And it's one of those things that on the quiz and on the final exam, I mark those, right? I read them. And so it's going to be 3 marks. Usually it's 3 marks out of 7 or 6. Okay, so it's a good chunk of marks, right? That's why we're here, to learn how to draw these conclusions. This kind of math that we're doing is not the point. Okay, so need to check all our boxes, right? First thing that we do in our conclusion is we need to compare our p-value to the alpha level. Okay, now we were given an alpha level, so let's go back there. Whee! And I'm going to seal this question blurb here, so I don't have to scroll that much again. So here it says use a significance level of 0.01, which means alpha is going to be 0.01. If it didn't say anything, right, then you would use 0.05. 0.05 is kind of the industry standard, what we use. Okay, so the first part of our conclusion, right, we have to compare, so just to recap, compare the p-value to the alpha level, 0.01 in this case. Then our conclusion in terms of the null hypothesis, you either have enough evidence to reject H naught or you do not have enough evidence to reject H naught. Those are your only options. Then you can state the conclusion in terms of the question, right? What does rejecting H naught mean for this question? All right, here we go. You're trying to show off and pull information from the question, right? And I always use the same setup, and you're welcome to use the same one, right? Just to make sure that you hit all these points. So first thing I'm gonna do is, since the two-sided p-value, right? Why not show off that you know it's supposed to be a two-sided p-value or a one-sided p-value if that's what it is, right? Why not? Of approximately 0, I'll go with that one, of approximately 0 or less than 0.0004, whichever one you, right, p-value of less than 0.0004 if you prefer to be kind of a little bit more particular. So tell me what type of p-value it is, one-sided, two-sided. Tell me what the p-value is, right? Is less than, of course, this is approximately 0, is less than the alpha level of 0.01, is less than the alpha level of 0.01. Again, you want to say what it is, right? Mostly to highlight that you know what it is, right? Okay. If the p-value is small enough, right? So in this case it's smaller than the alpha level, then we have enough evidence to reject H naught. Right? We have enough evidence.
This would be part 2, right?
Yes. Okay, I'm gonna, good job. Good job. Sorry. That was weird. That's part 1. I'll jot it down. So I will kind of summarize what the parts are after, but I want to make sure I have enough room here. So, all right, part 2, we have enough evidence to reject H naught, in favor of HA. I never do, but I guess you could be really fancy and you could tell me what the null hypothesis is and what the alternative hypothesis is. But I feel like there's enough to deal with here that you don't have to do that. I don't, because I guess I'm lazy. So here, let's do is the second part of the conclusion. Now, this question didn't really do us any favors in terms of asking the question in a nice way that could be rewritten as an answer. Often what I find is the question is kind of stated in a way that you could say, yes, there is evidence that the proportion of students get enough sleep is different from 0.5, right, or 50%. Here they kind of worded it in a weird way, but as long as you kind of try to formulate it in terms of the question, then I'm happy. Okay, so I'm just gonna go for it and say, therefore, there is a statistically significant difference from 50% in what? In the proportion of students, or the population proportion of students who say they did not get enough sleep. Weird, right? But therefore, there is a statistically, what am I trying to do? I'm trying to kind of steal as many parts of the questions as I can and kind of reword them so they make more sense. Statistically significant difference from 50%, or if you prefer 0.5. But when we're talking, right, we're pretty flexible in moving between proportions and percentages, right? So there's a statistically significant difference from 50%, and I stole that from where? I stole that from here. There is a statistically significant difference from 50% in the population proportion, right? Because our conclusion is always in terms of the population proportion, right? Or the population, right? Population proportion of students who say they did not get enough sleep. So this is going to be the third part of the conclusion, which is in terms of the question. The trickiest part, I think, usually, and the part that people love to forget, but you have to do it. Okay, so just to recap here. First thing we do is we have to compare the p-value to the alpha level. Second thing we do is your conclusion in terms of H naught, right? We did all our testing assuming the null hypothesis is true, and so our conclusion has to be in terms of H naught. Conclusion in terms of H naught. And then finally, the conclusion in terms of the question. Now, because I'm reading these, right, and marking them, if you mess up and you tell me that the p-value is less than the alpha level, even if it isn't, right, as long as you follow through with what that means in terms of the null hypothesis, and then what that means in terms of your conclusion, then I can give you most of those marks, right? And so just be consistent. Yeah. Right, for example, if you said, since the two-sided p-value of approximately 0 is not less than the alpha level of 0.01, that's wrong, right? But if you followed it up with, we do not have enough evidence to reject H naught in favor of HA, or just we don't have enough evidence to reject H naught, right? Therefore, there is not a statistically, right? So if you just follow through with what you said initially, then that's going to keep the most amount of points. Right. So that's hypothesis testing. Crazy, right? I know. It's terrible, but only in the beginning, right? Once we see other types of questions, we're going to apply this framework to all the different types of questions, right? So then we're going to get really good at doing hypothesis testing, but it is a lot in the beginning, right? It's a lot to keep track of.
Can you go back to step 3 for me, please?
Yes.
I understand the math
Wait.
behind timesing the Z value by 2.
Okay.
But why are we timesing by 2 if the Z value is 8.9? Why do we also need the negative Z value?
Because it's a two-sided test. So if it was a one-sided test, so if I wanted to use 0.7225 to show that it's significantly greater than 0.5, right? Then I would be good with just the one-sided p-value. Right? But because I want to show that there's a difference, then my sample proportion happened to be on the upper end, right? But it could also have happened on the lower end.
So we're assuming something could have that same level of extremeness could happen on the other side?
Exactly,
Okay.
if you want to test for a difference. So it's kind of the safest test because you're not making any assumptions, right? I've seen there are some decoy questions where they would get you to see if 0.7225 is significantly less than 0.5, for example. You would not have enough evidence to reject H naught, right? Because what would your p-value be? Be all this area, right? If it's less than, that's sneaky, right? But right, you can only use 0.7225 to test for a difference, right? By kind of imagining that it happened on the other end, or if it's greater than 0.5, right? Good. All right. So we've done all this work, hypothesis testing. Obviously, we need to practice, but there are a couple of things that I want to introduce to you before, well, before we end. When you're doing this hypothesis testing and you're making your conclusion, so you find that you have enough evidence to reject H naught, there's always a chance that you're wrong, right? You reject H naught and maybe you shouldn't have, right? Or if you fail to reject H naught, but you should have rejected it, right? Those are decision errors. Okay? And decision errors, I'll start that on a fresh page here. Luckily, there are only two types of errors that we could be making, right? And I like to summarize them in a table, which I'm going to steal from the textbook, but I'll also give you the definitions if you find that that's helpful. Okay? But let's just kind of lay the groundwork here. So when we conduct a hypothesis test, and either reject H naught or fail to reject H naught, remember, you never accept anything, right? So you either or fail to reject H naught, which we usually abbreviate FTR, H naught, fail to reject H naught. There is always a probability that we are wrong. A probability that we are wrong. The sneaky part is we don't know if we're wrong, right? And that's kind of the tricky part. Oh. I know what you're thinking. What? testing hypotheses using confidence intervals. You can, but baby steps.
Is that what we just did?
Well, we didn't use a confidence interval. We used a test statistic. I know. Yeah, so I'm gonna just skip that for a little bit. But guess I could tell you what it is, right? Either we're in the 5% of the tails, right, as a default. The alpha level is 0.05. So then we've got an area of 0.05 in the tails, or, right, the alternative would be I could build a confidence interval. And if the null hypothesized value is outside that confidence interval, right, 95% confidence interval, then I can reject H naught. But don't worry, we will do that more properly. Okay. So I like to kind of just memorize a version of this table, right? You might want to make it a little bit shorter, but you've got your test conclusion, which is our conclusion. You either fail to reject H naught or you reject H naught. But then we understand that we could talk to every student at that university and we could, in theory, ask them, did you get enough sleep or no? Right. And so we could find a population proportion, right? It exists. I think we're okay with that, but we don't know what it is. It defeats the purpose of what we're doing here. Okay. And so there is some truth though, right? But we will never know the truth about the population. The truth about the population. But H naught is either true or the alternative is true. And so, right, just it exists right out there. And so if I fail to reject H naught and H naught is true, then that's not a mistake, right? That's fine. But if I've rejected H naught, but H naught should not be rejected, that's what we call a type 1 error. Okay. So we can make a type 1 error if we're rejecting H naught. Right? If I rejected H naught and HA is true, then that's fine, right? That's not a mistake. Whereas if I fail to reject H naught, the error that I could be making is what we call a type 2 error, right? So I fail to reject H naught when HA is true. Okay. Let's just kind of, so like I said, I like this table, or I like to memorize some version of that table. Okay. Or if you prefer just nitty gritty definitions, I'll give you the briefest one possible. Type 1 error is rejecting H naught when we shouldn't have. Rejecting H naught when we shouldn't have. Before we conduct any hypothesis testing, we decide on our significance level, the alpha level. And what we're actually doing is we're establishing the probability of making a type 1 error that you would be okay with. So the default is 0.05, right? In the previous question, they used 0.01, so a little bit smaller, making it harder to make a type 1 error, right? And so the significance level, or if you prefer, you can call it the alpha level, which it is a predetermined probability of making a type 1 error. Is a predetermined probability of making a type 1 error. So we're basically saying, okay, at this point, I'm okay with making a type 1 error. If making a type 1 error is going to be really expensive, whether that's financially or time or just kind of resources, right? So expensive kind of encompasses a lot of things, right? You can lower the alpha level, but you can't go to 0, right? Because you'll never have a tail area of 0, right? And so you can't lower it too much. Has to be kind of a reasonable bound. So what we can say is we can lower the alpha level in an attempt to avoid, not really avoiding them, but lower the probability, avoid type 1 errors. So the significance level, we do have some control over. Whereas a type 2 error is when you fail to reject H0 when it should be rejected. Failing to reject H0 when it should be rejected. That's harder to control for. What does that mean? Means that there is a significant difference here, but you weren't able to pick up on it. Usually that's only due to your sample size being too small. That's really the only way to avoid type 1 errors. Usually not something we have control over, right? And so, but if you fail to reject H0, it's a really good kind of more funding opportunity, right? Oh, I failed to reject H0, but if you give me more money so I can collect a larger sample, then I might be able to get you something. It's all about that funding. So this is usually due to small sample sizes. So often for these types of questions, you'll be given kind of a question scenario, and then what does making a type 1 error mean in this case, right? Well, it means that you have rejected H0 and have, right? And so for us, right, in our example, we decided to reject H0, and there's a chance that we were wrong, right? But what does making a type 1 error mean in this case? It means that we said that the proportion of students who say they don't get enough sleep is significantly different from 50% when it's not. Oh my gosh, call the authorities, right? So that's what it would mean. So that's not life or death, right? Our conclusion here. But there are scenarios where it's really important that you don't want to make a type 1 error. There's a classic example of someone's on trial, right? You're either convicting an innocent person which would be a type 1 error, right? Everyone's innocent until proven guilty, so then you rejected H naught when you shouldn't have, right? Sent them to jail when you shouldn't have, or letting a guilty person walk free would be a type 2 error. That one, I usually have a hard time wrapping my head around that one, so I don't, but I'm sure it's in the textbook. It's in every textbook as an explanation of type 1 and type 2 errors. Okay, the last thing I want to do today, it was a lot. It was a big day today, big day. Chapter 5 introduced us to confidence intervals, hypothesis testing. Well, we started with the sampling distribution of p hat, right? And so now we're kind of into chapter 6. 6.1 does a recap of confidence intervals and hypothesis testing for one sample proportions. So I'll leave that alone. The only new thing that I want to bring up from there is calculating sample sizes. Seems useful. So I'll put it on a fresh page here. Chapter 6 is inference for categorical data. Six 6.1 is called inference for a single proportion. A single is really one sample, right? I call these questions one sample proportion questions. But this is really just a recap of chapter 5. And like I said, the only new thing in 6.1 is calculating sample sizes. Well, it's all new, I get that, but for us, on my end, the only new thing in 6.1 is calculating sample sizes. If you're going to be collecting usually surveys and stuff like that, right? But even biological data, right? Any sort of data, you want to have an idea of what sample size you're going to need, right? And so one of the ways that we can calculate what sample size we need is through this calculation. So before we collect any data, right, we need to decide what sample size before we collect any data. We need to decide what sample size will help us achieve some predetermined margin of error, okay, at some specified confidence level. Right? And so when we're talking about proportions, right, proportions are between 0 and 1. And remember, the margin of error is this plus minus chunk in the confidence interval. It's been a while, right? But in terms of proportions, right, usually 0.02 or 0.03 or 0.04 are kind of typical margins of errors that we want or are aiming for, and which is 2, 3, or 4%, right? If you think about it in percentages, at some confidence level, right? So I want to be reporting 95% confidence intervals, for example. Okay. So what sample size will help us achieve a predetermined margin of error at a specified confidence level. So this is going to be from the confidence interval. So we're going to recall that a confidence interval for p hat is plus minus p hat plus minus z star times the square root of p hat q hat over n. And this plus minus chunk is the margin of error. So you'll want to start your study and you want to determine, okay, what's a margin of error that you can live with? What are you going for, right? 0.03, let's say. And what confidence level do you want to be reporting at? The default is 95%, right? And so really, this confidence level is what gives us our Z star. But first, I want to say, okay, I'm going to need some notation for the margin of error. I'm going to use a lowercase m. Usually I like ME, but for solving formulas, a single letter is easier. So let m be the margin of error. Then m is this chunk, right? So m is equal to Z star times the square root of p hat q hat over n. And we want to solve for n. We want to solve for n. Okay. So I'm given some margin of error. I'm given some confidence interval or some confidence level, right? So I can rearrange this. And to start solving for m, I first have to divide both sides by Z star is the square root of p hat q hat, oops, q bar, q hat over n. And can undo the square root by squaring both sides. It's fine. M times Z or divided by Z star squared is p hat q hat over n. Okay. Good. I want to solve for n, which means I'm going to need to multiply it over to the left-hand side, but then divide this over to the right-hand side with a little bit of moving and shaking here. I get Z star divided by m squared times p hat q hat. Emily, there's a problem here. If I haven't collected any data, right, I don't have a sample proportion. Okay? So what we do is there are two scenarios. Okay? If I have a previous sample proportion that I could use, then I use that here, right? Then I use that as an estimate, okay? Because it gives me a pretty good idea of what to expect. Or if I have no clue and I want to maximize my n, then I'm going to use 0.5 as a conservative estimate, because you can play around with the numbers, but 0.5, so a 50-50 split is what gives me the largest value of n. And I know I'm out of time here, but if we have a previous sample proportion, we can use that as p hat. We can use that as p hat. if we do not, sorry, if we do not, we use p hat equal to 0.5 to give us a conservative estimate for n. And I'll say it now, but I don't have time to write it down, so I'll write it down next day. N has to be a whole number, so we always round up. Okay, I'll jot that down next day. I'll start there. If you have any questions, let me know. Otherwise, see you on Thursday. Stop this